All right, let's dive into these notes you've got here. Batteries, capacitors, electrical circuits, even semiconductors. You're really digging into the fundamentals here.
Yeah, it's fascinating stuff and something we encounter every single day without even really thinking about it.
Absolutely. So for this deep dive, let's unearth those hidden wonders of electricity, and maybe we can spark a little more appreciation for those invisible forces that frankly power our world. And what better place to start than with something we all know, something as simple as a battery. I mean, we've all used them, but your notes highlight something pretty amazing about something as simple as a D-cell battery. It contains something like 1.8 times 10 to the 24th power electrons. That's a lot.
It really is an almost impossible number to wrap your head around.
Hmm.
If you were to try to count that high, 1 electron per second, well, it would take longer than the entire lifespan of the universe.
Yeah,
And to think we just hold that kind of electrical potential in our hands every time we pick up a battery, it's pretty wild.
it is pretty wild. It really makes you appreciate how much charge is packed into such a small space. But of course, it's not just about the number of electrons, right? It's how those electrons are, put to work. Your notes mention how batteries convert chemical energy into electrical. It's that steady, reliable stream of charge.
That's really the beauty of a battery. It's like, well, we're thinking about the energy world. It's like the slow and steady marathon runner, right? Inside that D cell, you've got these carefully controlled chemical reactions happening, releasing that energy gradually over time. In fact, the total energy that's stored in a D cell battery is about, let's see, 4.32 times 10 to the fifth joules.
Okay, now you're just using big numbers to confuse me. What can you actually do with that much energy?
Okay. Imagine lifting a refrigerator to the top of a two-story building.
Uh,
That's about the amount of work that you could do with the energy that's stored in just one single D cell battery.
wow. That's a lot more power than I would have thought those little things have. But as you said, it's a slow and steady release. What about those times when we need a quick burst of energy? Something like a camera flash or a defibrillator? How do those work?
Ah, that's where capacitors come into play. So if batteries are the marathon runners, capacitors are the sprinters of the energy world, right? They store energy, not chemically, but electrically, by accumulating charges on two conductive plates. And these plates are separated by an insulator.
So is that kind of like static electricity, like when you rub a balloon on your hair, the balloon gets negatively charged and then your hair is positively charged, so then they, attract each other.
Exactly. And just like with the balloon and your hair, the opposite charges that are in a capacitor, they create an electric field between those plates. But here's the difference. Capacitors can discharge that stored energy way faster than a battery can, giving us those rapid bursts of power that you need for things like you said, a camera flash, or even a life-saving jolt from a defibrillator.
That makes sense. So we've got these capacitors, they're storing energy, kind of like a coiled spring, ready to release it in a flash. But your notes also mention resistors and how they play a role in these capacitor circuits. What do resistors actually do?
Resistors are all about control. Think of them like a valve on a water pipe. They regulate the flow. Without resistors, a capacitor could discharge its energy way too quickly and potentially damage other components in the circuit. Think about opening a fire hydrant full blast. You'd have water flying everywhere, right? You need a way to control that flow to make it useful.
Right, that makes sense. Control is critical when you're dealing with electricity. Speaking of control, your notes get into the nitty-gritty of how electricity flows through circuits, and they mention something that always kind of tripped me up. They mentioned that current flow is defined as going from positive to negative, even though the electrons themselves flow from negative to positive.
Yeah. It's one of those historical quirks about physics. Early scientists, they established these conventions before we actually fully understood what electrons were or how they worked. So even though we know now that electrons carry the negative charge and flow from negative to positive, we still use that conventional current flow from positive to negative.
So it's more of a convention than a literal representation of how electrons move.
Exactly. And as long as we keep that historical context in mind, we can still use the convention to analyze circuits effectively. I think of it like using a map that's oriented differently. As long as you know how to read it, you'll get to where you need to go.
Okay, that makes it a little easier to understand. So the electrons are flowing, the current is, conventionally flowing. And now let's talk about resistance. Your notes mention different sizes of wires. There's like 8 gauge, 10 gauge. What's the difference or what's the significance of that?
Ah, that's a great example of resistance in action. Okay, so think of it this way. Imagine you're trying to move a large crowd of people, right? And you're trying to move them through a narrow hallway versus a wide open plaza. That narrow hallway, it offers more resistance, right? It's going to slow things down. It's much easier to move through the open plaza.
Hmm.
And it's very similar with wires. A thinner wire, like a 10-gauge wire, it offers more resistance to the flow of electrons, while a thicker wire, like an 8-gauge, provides less resistance. It allows those electrons to move more freely.
So lower gauge number, thicker wire, less resistance. It's kind of like those high traffic areas where they widen the freeway to improve the flow of traffic.
Exactly.
So then why is it so important to manage the resistance in a circuit?
Well, resistance isn't just about slowing things down. It's also about controlling the flow of energy. Think about a toaster, for example. You want the wires in that toaster to have enough resistance so that they can convert the electrical energy into heat, thus, toasting your bread. But too much resistance, and the wire could overheat and break, or even worse.
Yeah, that makes sense. We need just the right amount of resistance to make sure that that current flows efficiently and safely. And this is where Ohm's law comes in, right? That nice little equation, V equals current times resistance.
Yes. Ohm's law is, well, it's fundamental understanding how circuits behave. It tells us how much current will flow through a certain resistance for a given voltage. And your notes have a perfect example. A 1.5-volt battery connected to a circuit with zero point 0.5 ohms of resistance will result in a current of 3 amps.
So we can actually use Ohm's law to kind of predict how a circuit will behave, which is really essential when you're designing circuits, making sure they work correctly and safely. But now let's move on to something that I think is even more complex, semiconductors. Your notes mention silicon as being a big player here. What is it about silicon that makes it so special in the world of electronics?
Semiconductors, like silicon, are like the chameleons of the electrical world. They have this incredible ability to act as both a conductor and an insulator, depending on how we manipulate them. It's like having a light switch that you can fine-tune to adjust the brightness instead of just being on or off. That's really in how silicon is structured at the atomic level. See, pure silicon, it's a decent insulator on its own, but when you start introducing tiny amounts of impurities, a process called doping, we can actually change its conductivity dramatically.
Doping. Sounds like something you do to a baseball player to enhance their performance.
Well, you're not far off. We're essentially enhancing silicon's ability to conduct electricity, right? By adding these specific impurities. So, for example, you could add phosphorus, which has one extra electron compared to silicon. And this creates what we call an N-type semiconductor. And what this means is it has more negatively charged carriers that are available to carry that current.
So we're giving silicon an extra boost, making it more, I don't know, more eager to let those electrons flow through.
Exactly.
Yeah.
And we can also go the other way. We can create a P-type semiconductor. And to do this, we might add something like boron, which has one fewer electron than silicon. And what this does is creates what we call holes, and these act like positive charge carriers, attracting electrons and helping facilitate that current flow.
So by precisely controlling these impurities, we can kind of sculpt silicon's electrical properties, turning it into this incredibly versatile building block for electronics.
Yes. And this is where it gets really exciting. See, it's this manipulation of silicon's conductivity that allowed for the development of transistors and integrated circuits. Basically, it's the heart of computers and countless other electronics. I mean, without this ability to fine-tune silicon, the digital revolution wouldn't have been possible.
It really is mind-blowing when you think about it like that. We're taking this element from the Earth, and with just, I don't know, a bit of atomic tinkering, we're transforming it into the brains of our modern world. That's pretty incredible. And there's also another fascinating thing about semiconductors, at least to me. Their conductivity actually increases as the temperature goes up, which is the opposite of what happens with metals.
That's right. You see, in most materials, they become less conductive as the temperature rises, and this is because the atoms start to vibrate more, and it interferes with the flow of electrons. But semiconductors, they're different. As the temperature increases, more of those electrons in the semiconductor gain enough energy to break free from their atoms, and then they become available to carry the current.
Oh, so it's like we're giving those electrons a little extra kick just to get them moving.
Yeah, I like that. That's a great way to put it. And this temperature dependence, well, it's actually a really critical factor when you're designing electronics that operate under a wide range of conditions. Like, think about it. Your phone might feel a little warm when you've been using a demanding app, right?
Yeah, definitely.
Well, that's because those semiconductors are working hard. And as they heat up, they're actually becoming even better conductors.
Okay, so it's not necessarily a bad thing when your phone gets a little warm. It's just those semiconductors doing their thing.
Exactly.
Okay, that makes sense. Now, your notes also get into some specific semiconductor devices, things like diodes. And these are basically like one-way streets for electricity, right? So what's the secret sauce there? What allows diodes to control the direction of the current flow?
It all comes down to how we combine those p-type and n-type semiconductors we were just talking about. See, a diode, it's formed when you join a p-type material and an n-type material together, and this creates a junction. And at this junction, that's where the magic happens.
Magic.
Well, it's pretty close. So when you apply a voltage in a way that aligns with the flow of electrons, so from the n-type side to the p-type side, the diode allows the current to pass through. But if you reverse the voltage, if you try to, force the current to flow upstream, the diode blocks it.
So it's like a door that only opens one way. You can push through it easily in one direction, but you try to go the other way and it's not going to budge.
Yeah, perfect analogy.
Yeah.
And it's this unique property of diodes that make them so incredibly useful in so many different applications. Think about LEDs, light-emitting diodes. I mean, those things are everywhere.
Yeah, for sure. Our phone screens, traffic lights, LEDs have totally revolutionized lighting.
They have. LEDs were like a perfect example of how we've been able to harness the power of diodes. So they work on a really fascinating principle. When the current flows through that diode in that forward direction, electrons from the n-type side, they recombine with holes on that p-type side. And when this recombination happens, it releases energy. And you know what? That energy is in the form of light.
So it's like those electrons are, I don't know, jumping across a gap and then emitting light when they do.
You got it. That's a great way to visualize it. And the color of the light that's emitted, well, that depends on the specific materials that are used to make that LED. Each material, it has something called a band gap energy, and this determines the wavelength and ultimately the color of the light that's emitted. That's why you can have LEDs that shine in pretty much any color of the rainbow.
And LEDs are way more energy efficient, right, compared to the old incandescent bulbs.
Yeah, absolutely. Another huge advantage. LEDs, they convert a much higher percentage of that electrical energy into light, whereas those old incandescent bulbs, a lot of that energy was wasted as heat. And it's this efficiency that's a big reason why LEDs have become so popular in everything. Light bulbs, phone displays, you name it.
Yeah, it's hard to argue with that kind of energy efficiency. But, your notes also mention that it's important to use resistors with LEDs. Why is that?
Yeah. See, LEDs, they're very sensitive to current. If too much current flows through them, they can overheat and burn out.
Right.
And remember those resistors we talked about earlier, the ones that control the flow? Well, we use them with LEDs to limit the current, make sure that it's operating within a safe range so that the LED lasts longer.
So it's like a safety valve, for lack of a better term, to keep those LEDs safe from being, overwhelmed by too much current.
Exactly.
I see that your notes even have an example that shows you how to actually calculate the resistor value for a specific LED circuit.
Yeah, it's important to make sure that LED shines brightly without burning out.
Yeah.
You need to choose the right resistor value. You've got to consider the LED's characteristics and then the voltage that you're applying to it. It's a balancing act, really.
A delicate dance between giving the LED enough current to light up, but not so much that you damage it. Gotcha. Okay, so LEDs, super cool. But your notes also touch on another type of diode, and this one seems even more mysterious, at least to me, the Zener diode. What makes these things so special?
Ah, yes. Zener diodes, they're like the rule breakers of the diode world. So remember how we said that forcing current to flow in that reverse direction through a normal diode, it can damage it.
Yeah, like trying to push that door open the wrong way.
Exactly. Well, Zener diodes are actually designed to not only handle reverse current, but to handle it in a very controlled and predictable way. Now, under normal conditions, they act just like regular diodes. But when the reverse voltage across the Zener diode, it reaches a certain point, a certain threshold, we call it its breakdown voltage, the diode suddenly starts conducting in the reverse direction.
Wait, so they want to break down...
Well, in a way, yes. But it's not a destructive breakdown like what you see in a normal diode. This is called reverse breakdown. But instead of damaging the diode, what happens is when a Zener diode hits its breakdown voltage, it's going to maintain a very specific, a stable voltage across itself, even if the current that's flowing through it is changing.
So they're like, what, voltage regulators? They keep things stable even when the current might be fluctuating all over the place.
Right. And because of that, they're often used in circuits as voltage references, or even to protect other components from voltage spikes. Think of them like surge protectors, but for your circuits, They divert that excess voltage away, keep everything safe and operating within their limits.
Okay, that makes a lot more sense. They sound like they're essential for making sure that circuits operate reliably.
They are. And they highlight just how we can take a seemingly simple device like a diode, and by just carefully engineering its properties, we can create components with such a wide range of specialized functions.
Speaking of specialized functions, what about photodiodes? Aren't those basically the opposite of LEDs? Instead of emitting light, they sense it.
Exactly. Photodiodes, they're designed to be very sensitive to light. So when light hits a photodiode, it generates electron-hole pairs, very similar to what we talked about with LEDs. But instead of emitting light, what happens is these pairs create a current that we can then measure, which means we can essentially convert light signals into electrical signals.
Wow, so it's like they're converting photons into electrons.
You got it. And this ability to detect light makes photodiodes essential in all sorts of light sensing applications. Everything from solar cells, converting sunlight into electricity, to fiber optic communication systems, transmitting data as pulses of light.
Didn't you also mention that photodiodes are used in pulse oximeters? You know those devices that measure blood oxygen levels? How do they do that?
Ah, yeah. It's actually a really clever application of how sensitive a photodiode is to different wavelengths of light. See, both oxygenated and deoxygenated hemoglobin in our blood, they absorb different amounts of red and infrared light.
So by shining, both red and infrared light through your fingertip and then measuring how much of each wavelength makes it through.
Exactly. And that's where the photodiode comes in. It measures the amount of light that passes through. And then by analyzing the ratio of that red and infrared light that gets absorbed, it can tell you how much oxygenated hemoglobin is in the blood. That gives you your blood oxygen saturation reading.
Wow, that's actually really, really cool and incredibly important. Okay, so from solar cells to fiber optics to medical devices, photodiodes are everywhere and clearly playing a huge role in our, technology-driven world. But as fascinating as diodes are, I'm still kind of stuck on something else you mentioned in your notes. Piezoelectric materials.
Ah, yes. Piezoelectric materials. They're very interesting. They have this really cool interplay between the mechanical world and the electrical world. You see certain crystals, things like quartz, they exhibit this piezoelectric effect.
So the piezoelectric effect, it sounds like it's straight out of a sci-fi movie.
It might sound like science fiction, but it's very, very real. And it's all around us. Basically, when you apply mechanical pressure or stress to one of these piezoelectric materials, it generates an electric voltage.
Wait, so you're telling me you can squeeze a crystal and it'll create electricity?
That's exactly what I'm saying. And the reverse is true too. Apply an electric field to a piezoelectric material, and it'll actually deform, change its shape ever so slightly. And it's this two-way street between the mechanical energy and the electrical energy that makes piezoelectric materials so remarkable.
Wow. I can already see all sorts of cool applications for something like that.
Oh, absolutely. And their applications are really diverse. For example, piezoelectric crystals are used in ultrasound imaging.
Ultrasound? Really? How does that work?
Okay, so in ultrasound, you use a piezoelectric crystal to create those high-frequency sound waves that allow us to see inside the body. So by applying a voltage to the crystal, it causes it to vibrate really rapidly, and this generates those sound waves. And then when those sound waves bounce back, off of different tissues, different organs, they hit the crystal and generate a voltage that we can then use to create an image.
So the same crystal is sending and receiving the ultrasound waves, so it's converting electrical energy to mechanical energy and then back again.
Exactly. It acts as both a transmitter and a receiver, and it's all thanks to that piezoelectric effect.
Wow, that's amazing. Your notes also mention piezoelectric crystals being used in microphones, so is that the same principle?
It is. So inside a microphone, there's a thin diaphragm, and it vibrates when sound waves hit it. Well, this diaphragm is connected to, you guessed it, a piezoelectric crystal. So as the diaphragm vibrates from those sound waves, it puts pressure on the crystal. And what happens? It generates a corresponding electrical signal. And then that signal is amplified and sent to a speaker or a recording device.
That's so cool. They're like tiny little transducers converting one form of energy into another.
And they're incredibly precise, too. In fact, because of that, piezoelectric crystals are also used in all sorts of things, really sensitive pressure sensors, accelerometers. They're even used in some high-end watches to help keep incredibly accurate time.
Wow, that's wild. They really are versatile. But as amazing as piezoelectrics are, we can't forget about superconductors. You mentioned them briefly in your notes, and honestly, they sound like they're straight out of Star Trek. Zero electrical resistance. It's honestly hard to even imagine.
I know. Superconductivity It really is one of the most mind-boggling things in all of physics. Imagine a world where electricity can flow with absolutely no loss of energy. There's no heat generated, no resistance whatsoever.
It sounds too good to be true.
It really does, doesn't it? But it's a real phenomenon. The catch is, it typically only happens at extremely low temperatures. I'm talking about temperatures approaching absolute zero, which is, well, it's colder than anything that's found naturally here on Earth.
Okay, so then these superconductors, what are they exactly?
So they're materials that, when they're cooled below a certain critical temperature, exhibit zero electrical resistance. It's like the electrons inside are no longer bumping into anything, you know? They flow effortlessly without any loss of energy.
That's incredible. But if it only works at such low temperatures, how can we even use them for anything?
Well, that is the challenge, and that's where a lot of research is focused these days. Finding or even developing materials that can exhibit superconductivity at temperatures that are a bit more practical. But even with the limitation of those extremely low temperatures, superconductors are actually already being used for things today.
Like what?
Well, one of the most well-known applications is in MRI machines, those big medical imaging devices. MRI machines use these really, really strong electromagnets, and those are used to generate those detailed images of our insides.
And those electromagnets, those require a ton of electricity to operate, right?
They do. And conventional electromagnets, well, they would lose a lot of energy as heat because of the electrical resistance. It would make them pretty much impractical to use for MRI. But with superconducting magnets, we can run huge amounts of current through them, and we don't have to worry about any energy loss. That allows us to generate those crazy strong magnetic fields that you need for something like MRI.
That's really amazing. So even though, we haven't cracked the code on room temperature superconductivity just yet, it's still exciting to know that we're already reaping some of the benefits of this incredible phenomenon.
For sure. And the potential applications of superconductors, especially if we can achieve it at higher temperatures, it's revolutionary. Imagine ultra-efficient power grids, transmitting electricity with almost no loss. Or what about super-fast levitating trains? Even computers that are so much faster, so much more powerful than anything we have today. It's really exciting to think about.
Yeah, it sounds like superconductors could completely transform our world.
They could. It's a field of, it's constantly evolving. Who knows what the future holds?
That's true. Okay, so we've covered a lot of ground here, from the ins and outs of diodes to this crazy world of piezoelectrics, and then the incredible promise of superconductors. But let's not forget about those large audio capacitors that we were talking about earlier. Those things store a surprising amount of energy, right?
They do. Those big capacitors, the ones you might find in a high-end sound system,
Yeah.
they're like the heavy lifters of the capacitor world.
Mm.
I think your notes mentioned that a 2 farad capacitor charged to 12 volts could store something like 24 coulombs of charge.
Yeah, that's a significant amount. To put it into perspective, that's roughly the total charge of all the electrons in a lightning bolt.
Really?
Yeah. Now, obviously, the energy is released much more slowly, much more controlled in a capacitor, but it gives you an idea of just how much these things can handle. And we're not just talking about theoretical potential here. Your notes calculated that the energy stored in a capacitor like that would be about 144 joules. Didn't we say earlier that's enough to lift a refrigerator?
We did. And look, I'm not recommending anyone try to use capacitors to lift heavy objects.
Right.
But it does emphasize that these things are not to be taken lightly, both literally and figuratively.
Yeah.
You have to remember, mishandling a charged capacitor, it can be dangerous. It's like having a coiled spring that's ready to release all of its energy in one go. You really do need to treat it with care and respect.
So safety first when dealing with capacitors, especially those larger ones. Always make sure they're properly discharged before you go tinkering around with them.
Always.
You definitely don't want to become a human conductor.
Nope. Not a good idea. But speaking of, respecting the flow of electricity, we've talked a lot about the individual components, batteries, capacitors, resistors, diodes. But the magic really starts to happen when you start connecting these things together, right? You start creating circuits.
Exactly. And we've talked about some simple circuits, but your notes get into more complex circuits where you've got multiple resistors, different configurations, you've got series, you've got parallel. It seems like things get a lot more interesting, maybe even a little counterintuitive when you start combining resistors in these different ways.
They do. When resistors are connected in series, one after the other, it's like, well, you're adding more obstacles for that current to flow through. Each resistor, it adds to the overall resistance, so it becomes harder for that current to get through.
So the more resistors you have in series, that means less current is flowing through the circuit.
Exactly. Imagine a highway. If you keep adding more toll booths, what happens? It slows the flow of traffic. But here's where it gets a little bit more interesting. When you connect resistors in parallel, it's a totally different story.
Oh, how so?
Okay, so in a parallel configuration, each resistor has its own separate path for that current to flow through. It's like taking that same highway and adding more lanes. It gives the traffic more options, and the flow is a lot smoother.
So you're saying that adding more resistors in parallel actually makes it easier for the current to flow, so the overall resistance of the circuit actually goes down.
You got it. It seems counterintuitive at first, but it makes sense when you think about it. Each additional parallel path that you add, well, it provides an alternate route for that current, so it reduces that overall resistance.
Oh, okay. I think I'm starting to get it. That's really interesting. And I see that your notes actually have those formulas for calculating the equivalent resistance for series and parallel circuits. Super helpful.
Yeah, those are really important. Those formulas are key to understanding how these more complex circuits work. They let you simplify a circuit with multiple resistors down to an equivalent circuit, but this one just has a single resistance, making it way easier to analyze and figure out how that current's going to flow.
Okay, so essentially, by understanding these, series and parallel circuits, we get a much deeper understanding of how electricity is distributed and controlled in pretty much all the electronic devices that we use every single day.
Exactly. Those two simple concepts, those series and parallel connections, they really do underpin the design of everything from the circuits in your smartphone to the massive electrical grids that power our cities. It's pretty amazing.
It really is. I mean, it's just incredible how those fundamental principles, even though they might seem abstract when you first learn about them, they translate into these real-world technologies that we rely on every single day.
It's the beauty of physics. And the journey of discovery, well, it certainly doesn't stop here. As you continue to explore, I know you will, you'll just keep uncovering more fascinating stuff.
You've definitely given me a lot to think about. I have to say, from counting electrons in a battery to the incredible potential of superconductors, this has been one electrifying deep dive.
The pleasure was all mine. Keep those questions coming. And remember, the world of electricity, it's full of surprises.